All right, so this is the equation for exponential growth. Y is the final amount. So that's what you get at the end. A is the initial amount. So that's how many you started with, or how much you started with. R is the rate of change. And we use it as a decimal. Is that green dark enough? No? No? Okay, let me change it.
Yeah, that's a little better.
We use a decimal here, so if it's a percentage or a fraction, we want to turn it into a decimal. And then T is the time, or, you know, over a period of how long something is going for. Okay. How do we use this equation? Okay, so we have a radio station is sponsoring a contest. The prize begins as a $100 gift card. Begins. So this would be A. Okay, once a day, a DJ announces a name, and the person has 15 minutes to call. If they don't call within that time, the prize, that's supposed to be an I, the prize increases by 2.5%. So this 2.5%, that's the rate, so that's R. Okay? So we want to write an equation to express ION. Wow, I can't type. Okay, write an equation to represent the amount of the gift card after T days with no winners. Okay, so T is the days. So we have our final amount. Our beginning amount is 100. Hold on one second. All right, so our initial amount is 100. And then we have 1 plus our rate. So now we need to take that 2.5% and we need to convert it to a decimal. So in order to do that, we move 2 places to the left. So that's 0.025. And then to the power of t. We don't know what t is yet. And 1 plus 0.025 is 1.025. So we add these together. How much will the gift card be worth if no one wins after 10 days? This is t. So I'm going to plug in, and I have 100 times 1.025 to the 10th. Scientific calculator, you'll do 1.025, that little caret top thing, and then 10, and then enter. If you don't have a scientific calculator, you have to multiply 1.025 times 1.025 10 times. Okay? So, what you'll get...
I got 128.008.
Yeah, I'm just going to put that in. Okay, and then you multiply that times 100 and you get 128.008, but we're just going to say round it to the nearest dollar because we're talking about a gift card, so it would be worth $128 at that point. So, compound interest uses, very similar to the exponential growth. Okay, the equation for compound interest is A is the current amount. P is the principal, or the initial amount. Like, that's how much you deposited into the account. Or if you're talking about a loan, that's how much you borrowed. R is the annual interest rate. N is the number of times the interest is compounded. And that's per year. And that N is there, and you also have an N right here, right? You have two N's. And then T is time in years. So this is, I'm going to say N here so that you know it's the both ends. Okay, now compounding. What does that mean? Is this is the number of times per year that the interest is figured out or calculated. Now, if you have like a home loan or a car loan, you're usually talking about monthly. So it's usually compounded 12 times a year, which means they charge you interest 12 different times a year based on the principal, which is the amount that you still owe. That's why it takes so long to pay off a house or a car. Okay. Like if you borrow $10,000 for a car and you borrow it for 5 years, you don't just pay $2,000 a year and you're done, right? You pay all this interest and they charge you interest every single month. And so for the first year or two that you're paying for the car, you're just paying for interest. And then you start to pay less interest and more car payment, and then eventually it's paid off. Same thing on houses. Compound interest, very good if you have a bank account and you're trying to earn money. Really bad if you borrowed money. Okay? So how does this work? Okay, Maria's parents invested $14,000 at 6% per year compounded monthly. Okay? So $14,000, that's the principal. That's P. 6% is R, monthly. Okay? How many months are in a year? 12. So you're going to get N equals 12. And then 10 years is T. So I'm going to take that and I'm going to plug it in. So I have 14,000 times 1 plus R. Well, R is 6%, so that's 0.06. So I have 0.06 divided by 12. And that's to the 12 times 10 power. Okay, so .06 divided by 12 is 0.005. And then that's the power of 120. Now you really would want a scientific calculator to do this. If you don't have one though, let me show you what you can do on the computer in just 1 second. Okay, so at the end of 10 years, if they don't touch it, you know, they didn't pull any money out or anything, they would have $25,471.55. So in 10 years, they've earned a little over $11,000. Okay, now what I want to show you, okay, let's say, oops. Let's say you don't have a scientific calculator. If you go on your computer, you do. And we can do, okay, and that would be here, that XY, and then I put in 120, and that gave me the 1.82. I just rounded it. Okay. So you'd push this XY button right here. Okay, so if you don't have a scientific calculator, you can use any calculator on a computer. You just view, it would be normally on standard, so you just go to scientific, and then you have that button, that XY button. Okay? All right. Question? So, okay. Exponential decay. Now, exponential decay, if exponential growth is growing, decay is decreasing, right? And if you think about it, when things decay, they decrease down into a pile of, you know, goo or whatever. So the equation for exponential decay is basically the same as for exponential growth. This is the final amount. So y is the final amount, a is the initial amount, r is the rate of decay, or actually still rate of change. That's what we called it before, so we'll call it rate of change still. And T is the time. The only difference between the two is this right here. In growth, that's plus, and in decay, that's minus. Otherwise, it's the same exact equation. Okay, and I mean, it makes sense, right? If you're decaying, you're decreasing, so you would subtract as opposed to add. Okay, so a fully inflated, this word right here is raft. You have it on your paper. Okay, a fully inflated child's raft for a pool is losing 6.6% of its air every day. If the raft originally contained 4,500 cubic inches of air, we're going to want to write an equation to represent that loss. Okay, so 6.6% is R, and that 4,500 cubic inches of air is A. Okay, we want to turn R into a decimal, so it's 0.066, because we move it 2 places. And then we add it together. And we get 4,500 times 1.066 to the power of t. And if we want to figure out how much air is left in the raft after 7 days, well, the 7 days is our t, so we're going to put a 7 there. get 4,500 times, oops. Hey guys, catch my mistakes. That's not plus. That's minus. So that's not 1.066. That's 0.934. Remember, if you catch my mistakes, extra credit. So this is not 1.066 either. That's 0.934. So I have 0.934 to the 7th. And I get 0.62, and then there's a bunch of zeros and some other stuff, but I'm just going to make it 0.62. And that means at the end of 7 days, there would be 2,790 cubic inches of air. Okay. So it would pretty much be halfway deflated at the end of 7 days. Does that make sense? Alrighty. For next, we have geometric sequences. Okay, now I feel like I want to take a little time, so I'm going to put in an extra slide. You can just make notes off to the side if you need to. There are two types of sequences. There's arithmetic, which you may have heard. Oops, there's no E in there. Arithmetic. I can't spell either. Okay, arithmetic, which you may have heard of as somebody pronounced it as an arithmetic sequence, because you spell arithmetic and arithmetic the same way, but it's actually an arithmetic sequence. And when you have an arithmetic sequence, you are adding or subtracting the same amount each time. Okay, so an example would be like if I go 2, 4, 6, 8, 10, etc., I'm adding 2 every time. Right? Does that make sense? I go plus 2, plus 2, plus 2, plus 2, and I'd keep going forever, and I would keep adding 2. Or if I had one where I like started with 55 and then I go down to 50, 45, 40, etc., 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 I'm subtracting 5 each time. Okay. A geometric sequence So a geometric sequence, you're multiplying or dividing the same amount each time. Okay, and division is actually, you don't write it as division, you write it as multiplying by a fraction. So instead of saying I'm dividing by, like if I'm dividing by 3, would be written as 1 over 3. If I'm dividing by 5 every time, I would write it as 1 over 5. And like as multiplying by 1 over 3 and multiplying by 1 over 5. Okay. So an example of a geometric sequence, let's keep with my 2's, except instead of adding 2 each time, I'm now multiplying by 2 each time. Okay. So just, since we're going to talk about geometric sequences, I want to make sure you understood the difference between the two. And then you can have like random sequence, or even a sequence that's not random but is not geometric or arithmetic. Like you can have a sequence that you know, like times 2 add 4. But that's not geometric or arithmetic. It's kind of like a combination of both. So those wouldn't have a name like this. Okay, so does everybody have this? Here, I'll pause. Okay, so now let's go back. So we have geometric sequences. Now, the arithmetic sequences could start with 0, because when we just add something to it or subtract something from it, you can start with 0. But we can't start with 0 on a geometric sequence, because if I start with 0 and then I multiply by anything, it's just 0. So my whole sequence would be just 0, which doesn't work. So we start with a non-zero number, and then each subsequent number, so every number after that, is a multiple of the previous number by the same ratio. So here we go. We determine if it's arithmetic, geometric, or neither. A good way to do that is we take this number here and we put it over this number here. So we're going to do 128 over 256. And then if we reduce that, we get 1/2. And then we do 64 over 128. And if we reduce that, we get 1/2. And then we do 32 over 64. And if we reduce that, we get 1/2. We're getting 1/2 each time. So the ratios match. So yes, geometric. Okay. The other way you could do it is if you could look at it and you know to divide by 2. If you see that, if you can see that you're dividing by 2 every time, you can just say, oh, you're dividing by 2 every time, so it is geometric. But if you don't see the divide by 2, you can do it as fractions. Okay, to go from 4 to 9, is there anything I can multiply 4 by to make it a 9? Well, we check. If I do 9 over 4, does that reduce to anything? If I go 12 over 9, that actually would reduce to 4/3. And if I do 18 over 12, that reduces to, 3/2. So I have 9/4, 4/3, 3/2. They don't match, right? So not geometric. Now I'm going to look to see if it's arithmetic. To go from 4 to 9, I add 5. To go from 9 to 12, I add 3. To go from 12 to 18, I add 6. I'm not adding the same thing every time, am I? So we also aren't arithmetic. So it's neither. Okay. From 1 to 3 times 3. Or again, I can do 3 over 1, which gives me 3. From 3 to 9, if I see it, yeah, times 3, or I can say 9 over 3 equals 3. Either way, you can do by multiplication or by figuring out the ratio, but it's times 3 each time, so it is geometric, because we're going to multiply by 3 every time. Here, there's not really a ratio. If I do 15 over 20, I'm getting 3/4, and if I do 10 over 15, I'm getting 2/3. So there's not a ratio, but if I go from -20 to -15, I added 5. And if I go from -15 to -10, I added 5. And if I go from -10, so I add 5 each time. So it's arithmetic. All right. Now, to find the next 3 terms in the sequence, we first have to determine what's happening. To go from -4 to 1 to -4, I multiplied by -4. And to go from -4 to 16, that's also -4. So I'm multiplying by -4 each time. Right? So to find the next 3 terms in the sequence, I multiply by -4. So I do -64 times -4. And that's going to give me a positive 256. And then I do positive 256 times -4. And I get negative 1024. Times -4 gives me positive 4096. Okay, so these are my next 3 terms. So if I keep going, I get my next one's 256, then negative 1024, then 4096. Okay. It's 1/3 if I do 3 over 9. If I do 1 over 3, it's 1/3. And then 1/3 over 1 is 1/3, right? So I'm multiplying by 1/3 each time. And here's why the ratio thing is kind of nice, because if you realize you're dividing by 3, then you have to go, okay, 1/3 divided by 3 and figure that out. Well, if I know I'm multiplying by 1/3 every time, I can just multiply by the 1/3. So my next 3 terms are 1/9, 1/27, and 1/81. All right. Now, finding the nth term in a sequence. Nth term just means some term, they haven't given us the number. This n could be 5, 10, 50, 700, whatever. Okay. Well, finding the next 3 terms is easy. You just multiply by whatever 3 times. But if we wanted to find the 40th term in a sequence, you'd have to multiply by whatever number was the difference Like let's say you're multiplying by 3 each time, but you'd have to do that 40 times, possibly. That's ridiculous. So the equation to find the nth term, and I don't know, that looks a little smushed. Is it bad on your paper? Okay. I'm going to rewrite it a little bit more spaced out. Is that better? Okay, so a to the n is your nth term, whatever term you're looking for. A to the 1 is the first term, or a sub 1 is the first term. R is your ratio of change, so what you're multiplying or dividing by every time, but written as a fraction. Then n is your like if we were saying the 40th term, n is going to be 40, and then you subtract 1 from that, and that's your exponent. Okay. So how do we use this? All right. We have this sequence: -6, -12, or sorry, +12, -24, +48. Can you see what I'm multiplying by every time? If it doesn't jump out at you, do the ratio thing. And just, you only have to check like 24 of them. Yeah, just check like 2 of them to see if it works, make sure it works. So -2. This is R. Okay. A to the n, that's what number you're looking for, so that just stays a to the n. And the a's are like the letters, so this would be a1, a2, a3, a4, and a5, etc., going down the list. The a's just stand for like some number in a sequence. And then that sub number is what order they come in. Okay, so a to the n is the number we're looking for. A to the 1, that's the first number in the sequence, so that's -6. R is -2, and then we have n minus 1. So this is just for the nth term, so that's why we're leaving the n in there. Okay. Now if we wanted to find the 9th term, we'd set that a to the n is -6, -2 to the 9 minus 1. So that's -6 to the 8th. Or sorry, -6 times -2 to the 8th. So I'm going to take that -2. To the power of 8. Now, because it's an even exponent, I know it's going to be an even number. I don't really have to do the negative in there. I just have to do 2 to the 8th. If it was an odd, then I know it's going to be negative. So if it was like, say, 2 to the 9th, -2 to the 9th, I would just do 2 to the 9th, but make it negative. Does that make sense? Okay. Anyway, 2 to the 8th is 256 times -6. Gives me -1536. So if we kept going down the list, this would be the 9th term. We can do the same thing for the 15th. Again, because that's an even exponent, I know that my number is going to be positive. And if I multiply that by -6, I get negative 98,304. Now look at this. We only went 6 terms out, right? We went from the 9th to the 15th. We only went 6 more terms, and we went from 1,536 to 98,000. That's exponential growth, geometric sequences. They get really big. And this is just multiplying by 2, 15 times, basically. We take a 6 and you multiply it by 2, 15 times, and you get 98,000. So back to our original bacteria talk. If you started with 6 bacteria, and let's say every 1 minute they divide, in 15 minutes you'd have 98,000 of them. And bacteria divide faster than once every minute. But let's just say it's 1 minute. So you have 6 bacteria on your hand, let's say. In 15 minutes, you have 98,000 bacteria on your hand. Wash your hands. Questions on this? I mean, we could check it. We could just keep multiplying by 2 and go out 15 times and make sure we were right. But this is the formula. Promise. Works.